Hey, so now we've been talking about balanced chemical equations. Let's actually like use them to do some stuff, huh? Actually make some electricity. Real quick, don't worry about learning these guys. The only reason I bring them up is because some of our terms are named in honor of them. So Alessandro Volta, aka volts, if you are familiar with some of your electrical currencies, yep. And Luigi Galvani. Luigi Galvani was an Italian scientist and inventor. They were both working with electricity. Memory serves, they cut off a frog leg and attached it to two different metals, and the nerve would twitch. That was kind of how they first proved that there was actually a way to get electrical energy or energy released from two different metals. The only reason I bring them up is because we're going to use galvanic and volts as terms for some of our electrochemistry. And so that's why we give them a nod there. Cool. Electrochemistry. We're talking about batteries. We're talking about any apparatus that allows us to transfer electrons via an external connector. Couple of terms here. If I was taking notes, I would get 2 and 3. You don't have to put all of it, but voltaic or galvanic cells, there's those names. These are spontaneous. These are AA batteries. They make free electricity that we can use to do stuff to a point till the reaction stops and it's no longer spontaneous and your battery is dead. Air quotes. So voltaic, if you hear voltaic or galvanic, that means they're spontaneous. They produce free energy. An electrolytic cell means you got to put energy in. K would be non-spontaneous. K would be less than 1. Yeah. For voltaic, K is greater than 1. For electrolytic, K is less than 1, non-spontaneous or reactant favored. Those are the big vocab coming off this one. So voltaic or galvanic, those are spontaneous. Electrolytic are non-spontaneous. You got to actually put in some juice for these to go. And they both have applications. So for example, batteries, they are voltaic. Yay, we love it that our computer turns on. Although, how many of you would be able to get your computer to turn on right now? You guys still have juice at this time of the day? Probably not. Got some nose. You plug it into the wall and it turns into electrolytic. We actually force the electrons back so that the next time when you go to use our computers, it can be voltaic again. Ooh, that's fun. By applying electrical current, we can switch between them. Corrosion, buku bucks in chemistry and chemical engineering. A lot of money gets invested annually in how can I stop my boat from corroding, my hot water heater from corroding, my screws I use in my deckwear. All of these are corrosion protected, and there's lots of research that goes into that. Anytime you get chemicals, like I order from a chemical supplier, and I got to get reactive things. The problem is reactive things have already reacted on Earth. So I have to pay money to a company to shoot stuff with electricity, to turn it back into the reactive thing so they can ship it to me so you can re-react it. That's fun. That's how you get like pure sodium metal. You can't find sodium metal out in the environment. It's already reacted with water and oxygen to turn into sodium chloride or sodium oxide. We got to actually put electricity in to get it back. And then your biological electron transfer, I believe that's your sodium potassium pump, yeah. Excuse me. But yeah, or your electric eels. These are all voltaic processes. Anyway, got the terms. Voltaic, galvanic, spontaneous, electrolytic, non-spontaneous. Sorry, I just want to build a battery. Desert island stuff, right? When the zombies come, you know how to build a battery. They'll keep you in the colony. What? Sorry, no, more time over here. All right, people still writing. Oh, you never think about that? Like what your useful skill will be when the zombie apocalypse comes? Oh. You're going to know how to make electricity. You're going to know how to make a battery. That's a good skill. Also good. I can save life. Also good. Yeah, medical. Absolutely. There you go. right. In order to get a current that we can use to do work, we got to split them apart. So we're going to have one pot. One of our containers is going to have our oxidation reaction. It's going to lose the electrons. And then we're going to have one pot, one beaker that's going to have the reduction. And then we're going to make those electrons go through a wire. So that way we can like make those electrons do stuff for us. Make some electricity. So to obtain a current that we can use to do work, we got to separate the oxidizing and reducing halves. Don't worry about the agents. We're not using that vocabulary. And we separate them so that the electron transfer occurs via an external wire. We call that a battery. In your AA or AAA, what they do is they roll it up. It's like they make it into, well, it's a tube shape. You knew that. What they do is they roll it and then put a divider in between. So essentially it's still two separate halves. You got your positive and negative sides on your battery, but they've rolled it so that they can get more surface area to actually get more of a voltage going. So, acid assisted, you know that, battery acid. Cool. Yep, vocab. Oh boy. Last slide, you got it. This is it. So voltmeter, that's it. That's just measuring the volts you're making. That's here in the middle. We've got our external circuit or our wire that's going to run the electrons from the anode to what we call the cathode. And for my Faraday people, Michael Faraday was the one who kind of coined some of those terms, anode, cathode. So your wire is what carries the electrons from one to the other. Your anode is the place where oxidation is occurring. This is where mass is lost. Your cathode is the place where the reduction is occurring. This is where the mass is gained. And then your salt bridge is this thing in between that's just got ions in it. This biz in the middle, it's just got some ions in there. And if you got all those things, you can make a battery. Voltmeter just measures how much electricity is running through there. Wire is running the electrons. Anode is where your oxidation is occurring. Cathode is where the reduction is occurring. Salt bridge keeps the ions the same in both beakers. I will admit, vowels go together. Little mnemonic device or vowel trick here for you. So anox, they're both vowels, right? Oxidation at the anode. Oxidation at the anode. Red cat. Consonant. Reduction at the cathode. Reduction. Red cat. Reduction at the cathode. Oxidation at the anode. Reduction at the cathode. Anox. Red cat. and we often, and you didn't know you're doing this, I did it subliminally, right? We've been already splitting them apart into their two containers, right? I've done oxidation every time on the left, reduction every time on the right to get you kind of thinking about what's going on here in terms of our battery. We're gonna make one here. We've got zinc for our anode, and we got copper for our cathode. So what we're gonna do is we're gonna take a little piece of metal, little piece of zinc. We're gonna put it in to a solution of zinc ions. Oxidation is lost electrons. So our zinc is going to turn into Zn2 plus and give way to electrons. Here's our oxidation reaction. Ooh, but let's think about it. What's going to happen? I got my bar of zinc. Got this wire running over here, right? Our electrons are going to go through this wire, but every time we send two little electrons up, what happens on the surface of our anode? The zinc turns into what? Our zinc turns into zinc 2 plus. This one's solid, but this is aqueous. So over time, as we keep shooting electrons away from our zinc, more and more of this anode gets eaten away. And those zincs come off and start floating around in the soup. And so that's why we say that mass is lost from this piece of metal. Because as more and more electrons leave, more and more of the zinc goes aqueous. What's happening on the other bucket? The other beaker. You got copper. We got copper 2 plus floating around. It's getting, copper is getting reduced. It is, sorry, I should, gaining 2 electrons to turn into solid copper. Where's the copper 2 plus going to come from? The aqueous solution. So 2 electrons come over through the wire. They come down to the surface of the metal and they say, come here, copper. And one of our copper ions comes up and goes, I'm copper now. And it keeps doing that. So more copper builds up, more copper builds up, more copper gets plated and plated and plated. And over time, we build up more mass on the cathode. Ooh, but wait. This is going to break real fast. Because what's happening in this pot over here? What are we making? Aqueous solution of zinc. We're building up more and more 2 pluses, right? Over time, this solution is going to get crazy positive. And what's going to happen over here? The 2 plus is going away, so this is going to get more and more negative, yeah? What's the charge of an electron? Negative. If we get too many positives in our beaker over here, our electrons aren't going to leave anymore. They're going to stay over here with the super positive solution. And so what we do is we include a salt bridge. That's the purpose of the salt bridge. Right? Because in the salt bridge, we just got some salt. We don't care what it is. For our example in the back, I think I've got potassium chloride. Potassium chloride, which is just ions floating around. We got some K pluses floating around. And we got some Cl minuses floating around. Right? These are build up pluses, right? So the negatives, the chlorides come down to keep this beaker neutral. They cancel out all those positives we're making. And as these positives are leaving, the K pluses are coming down to replace them to keep this beaker neutral. So without the salt bridge, we actually don't make any electricity. Got to have that salt bridge in there. Got to have all the parts. How about that? Shall we make one? Yeah, let's make one. We'll talk more about why this actually does what it does and electromotive force and all that stuff. But we need some zinc ions. Zinc sulfate. Ta-da. There's some zinc ions. We need some copper ions. Copper ions, yay. We need some metals. Here's our strip of zinc metal. That goes in there. We need some copper. That goes in there. So going through the wire, through our voltmeter, back to the copper. What are we missing? Salt bridge. That's the fun little YouTube here. This is our fun little YouTube. So we're just going to take some potassium chloride. See if I can pour this. Whoa, I had a little airtight. Sorry, my cotton. Yeah, that's fun. Sorry, you just kind of want to keep it from diffusing too quickly. Sorry. Ta-da! Free energy. Oh, I guess proof in the pudding. So here is our volts. Again, I'm on hundreds. I'm on hundreds. I should do. There you go. 1.86 volts. It's not a lot. We're up on voltage. Sorry. People in the back. Full voltage. Ready? Here's the fun part. I'm just gonna pull the salt bridge out. Boop. Immediately dies. Kills it immediately. So it's nice to see how important that salt bridge is, because without it, you don't have neutrality within your pots anymore, and your battery dies. So what I'll do is actually, we've kind of seen the setup. I'll just connect one of these wires directly over, and we'll just let it run. And at the end of the unit, we can actually look to see if we should have copper plating onto this one. This one should get eaten up over time, and so we should be able to see the gain and loss on those electrodes, or on those electrodes, especially over spring break. Just let it cook for a whole week. See how much we gain out of this. Free energy. How we done? Cool. Ready for a take home quiz? Let's do it. Take home quiz.
Let me get a good look at this.
I mean, if you'd rather wait and do it in class.
Get a good look. What if I just pulled the salt bridge?
I thought this would be good.
Just do it. Just do it.
Don't worry. Number 2 says agents. Don't worry about it. You're not responsible for that.